Yeah.
All right, should we start? I think everyone is here, yeah?
Sure.
Yeah, okay, so it's my pleasure to welcome Konstantin Mischaikow, and he'll be talking about dynamic clades, the coarse approach to nonlinear dynamics. Yeah, thank you.
Right. So thank you very much for the invitation. So this is, I gave a talk in the Fields Institute symposium on I forgot even the title, dynamics and machine learning, or however it was called. So this is in some sense a prequel to that. I will kind of finish this talk with one of the motivating examples I gave for that. But since this is a dynamic systems seminar, I thought that everybody here should be interested in understanding dynamics. And so what I want to talk about are what I think are two fundamental problems with systems. All right, and so the whole point of this is to try to overcome these problems. And I'll try to make an argument that we need a different framework for studying dynamical systems. But I will also make sure at the middle part of the talk will be to argue that this new notion of dynamics that I'm introducing, how it relates back to dynamical systems. All right, because I think that's I love dynamical systems. This is an attempt to address problems with it, but not to give it up. All right, so the first case that I want to talk about is something that I think is a reasonable goal. This is especially in say a data science driven, a data-driven science world, we would hope to be able to do something like the following. So, imagine you've collected a time series data from a fixed experimental system. You've got lots and lots of the time series. I'm going to let you collect as much as you want. For as long as you want. And you have another experimental system, you're doing exactly the same thing. And it seems like, from a science perspective, if I allowed you in a reasonable way to collect as much data as you want, then you would have, if those systems are different, then eventually you'd like to be able to say, hey, these systems are different from the analysis, all right? Now, I'm not going to tell you what different is, because I think different probably depends very much on the to work with. But what I will say is that at least theoretically, the standard, the classical approach of dynamical systems will not allow you to achieve this reasonable goal in general. I mean, obviously there are examples you will, but in general you won't. And the reason is because we are studying extremely fine information. And for all of those people working in dynamics, I don't think this is a surprising theorem, but it is nice that it can be formalized. And what Foreman, Rudolph, and Weiss proved was that the collection of pairs of dynamical systems that are ergodic and conjugate is not Borel. Now, this is a set theory paper. For those of us who need translation, like me, fortunately they provide it in the paper. And here's a paragraph from their paper, basically saying that if we really want to be able to distinguish everything up to conjugacy, then we're going to need at least uncountably many different invariants. All right, and we're only collecting, from the reasonable problem, we're only going to be collecting countable amounts of data, and so this theorem in some sense says that there will be dynamical systems where you will not be able to distinguish them, even though from the classical notions of conjugacy that are at the heart, which are equivalent to studying invariant sets, will not allow you to will not be distinguishable from the finite data, even though they're different. And so the conclusion I take from this is that if we want to achieve this reasonable goal, then we can't focus on invariant sets as the fundamental object But I mean, I don't want to give up invariant sets. I just will try to argue that they don't need necessarily to be at the front and center, that we can still say things that I think all of us would find interesting. It's just that we're going to do it on a coarser level. Okay, so that was the first example. The second one, I think, is kind of unreasonable goal, but nevertheless something that I think we're moving more and more towards. I think it's unreasonable because I don't know that how it'll ever be resolved, and in the short run it definitely won't. And this, I would say, is kind of what I would call automated modeling. Obviously modeling involves some kind of physical system plus some level at which you want to understand that system. And if I gave you the picture on the left, the solar system, and I said, could you give me, tell me the location of the planets in the future, then we know how to do this, at least to a crude level, which is go out and find out where all the planets are right now, find out their velocities right now, measure their masses, and then Newton says, well, plug it into this equation and you'll get a pretty good approximation of what's going on. All right. So if we're on something like celestial mechanics, and we're not asking for what's going to happen in the infinite future, but we just want reasonable predictions, then we know how to model something like this. We have first principles rules that allow us to solve the problem. If we look at another type of problem, and again, I'm going to just start with a picture, and here's a picture of the EMT, of a version of the EMT network, epithelial mesenchymal transition network, which is something that's very relevant for oncologists these days. The details are unimportant. I don't know what equation to write down. And there's a reason I don't know what equation to write down, and that is because every one of these arrows in this diagram of these interactions is incredibly complicated, right? We have transcription, translation going on simultaneously, and there's tremendous complexity to each one of these steps. So this, excuse me, this diagram is representing a multi-scale system on lots of different scales, extremely complicated. And so we kind of have to, we can't get into all the details for our model. And so trying to write down, there's no first principles that we know how to get to for this kind of a system. But we would like, I mean, this is relevant for like I said, it is a hot subject in oncology right now. So we really would like to be able to understand the dynamics of this. So how do we do that? You could argue that the problem is we just need to go in and study this network in greater detail. But I want to argue that that's not. I don't think that's the most fruitful way to go forward. First of all, studying in detail is extremely expensive. Here's an example, the Lac Operon. This has been studied for probably 60 years now, maybe 70 years, in detail. There's more known about this network on kind of the biophysical level than almost any other network. People actually go to the level of doing modification on the DNA to do experiments. So, here's a network, and this is something where as much experimentation has taken place as possible. It's supposed to act as a switch. It's supposed to decide whether E. coli are going to eat glucose or say lactose, and so it's supposed to act as a switch. And if we think about switches, then we think about, at least I think about hysteretic switches, and this data right here is, that looks like a switch to me. All right. So you have a single stable state up here, you have a single stable state here, and we see kind of hints of the unstable equilibrium in between. So we have our bistable setting. This is from a paper coming out of Van Oudenarden's group in Nature in 2004. And this is, I think, an incredibly clean experiment. It can be done a little bit better using today's technologies probably, but for the point of trying to argue this is a switch, you can't, I can't imagine a nicer set of experimental data. The only thing I'd like you to observe is that this axis is a log scale, right? So these are log scale measurements. Now, in their paper, they write down a model for what's the dynamics that's generating this. One can quibble about, their particular choice of modeling, but that's not really what I want to do today. I want to just say, look, they've made a model, great, but then what do you do when you have this model? And they do exactly, they're biologists, so what's going to sound like criticism is really should be taken as criticism to the math community, not to the biology community, because we taught them differential equations and what you're supposed to do with equations. So here's the model. What do you do to take this model and match it back to the experiment? Well, there's two parameters in here, alpha and beta, and so you go and figure out what alpha and beta are. And so here's the value of alpha. Now, where I have problem here is that you see three significant figures, but this is a log scale. And when I think about log scales and significant figures, I think of losing significant figures rather than gaining significant figures, right? So rather than having three significant figures, maybe we should be having a -2 significant figures, all right? So the fixing of a particular parameter value to this degree of precision just doesn't seem reasonable with respect to the experimental data that we have. So I want to go back and I want to think about what does it mean when we think about an ODE model and we're trying to understand the ODE with respect to this kind of data. All right, so I have my data. What does it mean to solve an ODE? And I would say that abstractly, what Osbadok, Van Oudenarden are doing is they're doing what we've taught them to do, right? This looks like there's two equilibria. So you write down an ODE and you solve for two stable equilibria and the existence of an unstable equilibria, and then there should be a basin, there should be a separatrix, and so we have the two basins of attraction. Right, this is the classical dynamics that we've all learned. My comment about it is it's precise in the sense that I'm talking about fixed points. In their case, they went and actually solved literally for where those fixed points were so that they can match the parameters. But I claim it need not be an accurate representation. And so what do I mean by that? So let's pretend that this is actually the truth. Okay, so this is what the Lac Operon does, right? God came down and said, here is the Lac Operon. Now, as modelers, we come along and we make a model. And here's the model that we make. And I think in biology, if you could make a model that was this close to the truth, people would be very, very excited. So where do we lose accuracy? Well, at some point we have to measure parameters. So we go in and we make a parameter measurement, and here's where the parameter measurement is. And so our analysis says that our model says, well, there's one fixed point, whereas in reality there are three fixed points. Now, this should not come as a surprise. I mean, this is the basic problem of bifurcation theory. That's what a bifurcation is all about. A small perturbation in parameters leads to qualitatively different structures because the set of invariant sets change. So what's another way to think about this particular dynamics? How could I think about solving this ODE? So it seems to me that the primary issue here is identifying this bistability that becomes monostable. And so let's think about bistability. What, if I have to talk about the bistability to a layperson, or even if we talk amongst ourselves about bistability, what is it? Bistability is that, there's two different places you can end up. That if I said, well, I've got a dynamical system and I could end up in one place or I could end up in another place, I think most of you would accept that that's bistable. And of course, we know something from dynamics, from topology, that if this is a continuous system, then there has to be something in the middle that acts as a separatrix. So on this level, I can abstract bistability into a poset. All right, this is an acyclic directed graph. It's a poset. There are two minimum objects in this poset. Those we could think of as the stable regions, and then there's some kind of unstable object. So I'd like to think about this as being my solution to the ODE, just this poset structure. Well, there's something to be gained and something to be lost. I mean, this is not precise at all right? Because I'm not telling you, I'm just saying a poset, all right? So there's no precision. There's just that there are three potential recurrent regions, and there's dynamics from one of those recurrent regions to two other recurrent regions. But I claim that it can be turned into accurate statements. So let's go back to this, which is somehow the problem with accuracy, and how would it be represented in this poset structure? So if I was looking at this picture and talking about it from this poset structure, then here is where I see my bistability. Well, this is clearly the domains of parameters where you see bistability. Way out here, it's probably not hard to identify monostability. And of course, it's at the bifurcation points that things become subtle. And the way it would be represented in this graph structure, this poset structure, is that for these parameter values around here, you would see a poset containing two elements. What does this poset represent? Well, I don't know. It's just, it's an object. It's a warning flag that, something might be going on here. If I'm in the model situation, I don't see fixed points. If I'm in the truth, well, there are fixed points in there, but what would happen if I was actually running my biological system with this truth? In reality, there's also going to be some noise going on, and so this stable fixed point is, with time, probably going to get kicked out of this basin, and so we will end up at this much more stable fixed point. So what would we see? We would see the dynamics. It would slow down. It would hang out in this region, and then eventually end up down here. So, well, this is a region you want to study. That's all that this model would come back and tell you. So if you saw this kind of a set of graphs at these, light blue, I guess we call cyan nodes, these are the places where you might want to do more experimentation to understand what's going on. All right, so the point of this talk is to talk about this part, this poset structure. This is the Conley complex. What I don't have time to talk about would be how to put all this together. This actually has a sheaf structure, and I would say one of our current focuses of research is actually trying to figure out how to put all this together, not in the one-dimensional setting, but kind of in an n-dimensional setting. All right. So these Conley complex.
This word poset, what does it mean?
I'm sorry. What?
This term poset, what it is?
Oh, I'm sorry. Partially ordered set.
Okay, sorry.
Yeah, no, please interrupt me with questions. Don't apologize for asking the questions. I spend my life talking to the computer with minimal feedback, so please. All right. Okay, so this Conley complex is really, in some sense, what I'm after, and we will eventually get there. So now I need to take a step and do some, talk about some mathematical structures that I'm assuming not everybody is familiar with. The question of poset just emphasizes that. All right, so please bear with me as I go through this. I've tried to make it as painless as possible, and I will get back to dynamics as quickly as I can. All right, so here's a primer on order theory and algebraic topology. Okay, so I'm going to start with a bounded distributive lattice. So this is a set with, the way I'm thinking about it, it's a set with two operations on it, and then there's a minimal element and a maximal element. If you want a concrete example to think about a set X. The power set of it would be the L, and then we're allowed to take intersection and union. The minimal element is the empty set, and the maximal element is the whole set. All right, so this is the primary example, the archetypical example of a bounded distributive lattice. At some point, I will suddenly change these operations on you for a particular lattice. So I do need this lattice structure, the ideas of lattices. But for almost everything I'm going to talk about, you'll be okay if you just think about De Morgan's laws and intersection and union of sets. Bounded distributive lattices are special cases of posets, and the way the poset structure is that X is less than Y if and only if X wedge Y is X. That would be the definition of the inequality for the poset, for the partially ordered structure. The way to think about that is if we go back here, then the set X is a subset of set Y if X interset Y is X. All right. All right. For almost everything I'm talking about in this lecture, I'll be talking about finite bounded distributive lattices. If I really were, if this was a course rather than just this lecture, then I would be trying to understand much finer identifications of what I'm about to talk about and dynamical systems. And for that, I would really need to be working with infinite bounded distributive lattices. But for today's talk, I'm going to restrict to finite distributive lattices. So again, let me start with a finite partially ordered set, poset. I've used the word over and over again, and I finally tell you what it means. So here's my finite partially ordered set. If I give you a finite partially ordered set, there's a very natural way to create a finite bounded distributive lattice. And what that is the lattice of downsets. So I go to every element in my poset and I look at all the elements that lie below that element, including that element. So here is the set A. What lies below it? Well, okay, so there's the empty set. Nothing and everything below it, which is the empty set. There's A, which would be the set A, and everything below it, it's the minimal element, so below it is the empty set. B and everything below it would be A, B, etc. All right, so you look at that collection of all subsets of this set that are obtained from this lower than these downsets, and then take unions of them, and that produces a lattice. And so this is the lattice. So for example, you get A, B, B prime by taking the union of A, B and A, B prime. Okay, I started this slide with lattices. What I've done is said, well, if you give me a poset, I can produce a lattice. So let's go back and start with a lattice. So let's pretend we start, for example, with this lattice being handed to us. Can I get to posets? And the answer is yes. I told you that any lattice is a poset, but that's not the poset I want to focus on right now. I want to focus on a subset of this lattice, and this is the subset of joint irreducible elements. Here's a formal definition, but let me just say that what it really means is I've shown you the lattice with the, well, inclusion is the less than in this setting, because we're really working with a lattice of this structure. And I'm going to look at those elements that have a unique immediate predecessor. So the ones that I've labeled in red, for example, this has a a unique immediate predecessor, whereas this element here has two immediate predecessors. So this is this I mean, there is a partial order here, right? And so I by inclusion, I get back this partially ordered set, and this would be the poset of joint irreducible elements. And if you look at this poset structure, it looks very much like this poset structure, and that's not a coincidence. There's a fundamental theorem in this lattice theory due to Birkhoff, and what it says is that if I was to start with a lattice and I look at its poset of joint irreducible elements and I look at the lattice of downsets of that, I will end up with a lattice that's isomorphic to the one I started with. And likewise, if I start with a poset, a finite poset, and I look at the lattice of downsets, and then I look at the poset of joint irreducible elements in that lattice, then I'll end up with a poset that's isomorphic to the one I started with. So the point is that these two, by these transformations, are contain exactly the same information. Again, if I was trying to give you the general theory and I wasn't, so I had to go to the infinite bounded distributive lattices, then I should have been telling you about Priestley's theorem rather than Birkhoff's theorem. But again, for this talk, everything's going to be finite. So Birkhoff's theorem is sufficient. Okay, so what I've told you now is that we have these notions of posets, lattices, and a theorem that tells us how to go back and forth between them. Okay, so that was the order theory background. Now let me tell you a little bit about combinatorial algebraic topology. And I'm really starting a very, very combinatorial level. And so a cell complex consists of a poset, all right, together with two functions. There's a dimension function, and there's something called an incidence function. So it maps pairs of elements of this poset into, well, in most general, it would be a PID. For today, let's just assume that K represents a field. And in fact, if I ever have to, if anybody asks me any question where where this comes into play, I'll just choose Z2. All right. But these functions and the cell complex and this poset fit together by the following conditions. Dimension is a poset morphism. So in other words, there's this, we can talk about the dimension of cells, and that does not contradict this this order relation that I've put on the poset. If I look at two cells and I'm telling you that the incidence number is not 0, then what must be the case is that the dimension of this is the dimension of Xi is 1 larger than the dimension of Xi prime. And again, you satisfy this order relation. And the final condition is an algebraic condition, and that says that if I'm summing up, if I pick a Xi prime, Xi and a Xi double prime, and I perform this sum over all Xi primes, then I'm going to end up with 0. I'll come back to that in a moment. What should you be thinking of right now when I tell you about a cell complex? Think about a simplicial complex. All right, so you have a simplicial complex. You have, for example, the 2-dimensional cells. You have the 1-dimensional cells. You have the 0-dimensional cells. And then there's this incidence number. And if I'm using Z2 coefficients, then I just say, well, if this 1-dimensional cell is an edge of this 2-dimensional cell, then I will put a 1 as the incidence relation. All right. And so this Xi0 would have a 1 incidence relation with Xi1 prime, etc. This condition right here means that this cell complex generates a chain complex. And if you write out the matrix that's associated with this, that is your boundary operator for the chain complex. All right, so this is a purely combinatorial way of getting us into homology theory. More generally than a simplicial complex, everything I'm going to talk about today will work for regular CW complexes. All right. So, I'm in the end of the day, I'm going to be talking about spaces, and they can be, well, for me, a sufficiently nice space is a regular CW complex, a triangulable space All right, so these are fairly general spaces, but there are constraints that need to be put on them. Again, this is just a review from algebraic topology. If K is a field, then this chain complex that I'm going to produce is going to be a vector space. If this is not, down your alley, then just think that to every cell complex, I'm going to associate a vector space. And then when I start talking about homology, just realize that I've done linear algebra computations based on these vector spaces. All right, so we're working with vector spaces today for the chain complexes. So I talked about a post set, and the previous slide was all about how you move from post sets to lattices by looking at down sets. I don't want to let the last slide go to waste, so I make a remark. I can take the lattice of down sets of this post set, and that's fine. That's again a collection of sets now, but just taking this as a lattice is not going to give me cell complexes, all right? Because this is, the cell complex requires me to have the dimension function and the incidence function. However, I can talk about a lattice of subcell complexes of this cell complex. And what I have to do is I have to tell you what are the appropriate algebraic relations, all right? And so to define this lattice of subchain complexes, take any element of the down set of X, and now define the wedge between any two of those elements to be intersection. We're talking about intersection of vector spaces now. That's perfectly well defined. And the V operation is, well, take the span. So I have two vector spaces. All the basis elements for the vector spaces are coming from the elements of X. So it makes perfectly good sense to talk about the span. And so if you do this, now I get a lattice of, well, vector spaces. Okay. So we're gonna care very much about this lattice of vector spaces. And this is why we need this lattice structure, is because, here's a case, here's an example where these two algebraic operations are not just intersection and union. Okay, so one more definition. A lattice filtered cell complex. Okay, so this is a cell complex X, just like I gave the definition in the last slide, together with a finite distributive lattice L and a lattice homomorphism. All right, so think of the lattice as an algebraic object. You have the wedge and you have the V, and so if this is going to be a homomorphism in that category, then lambda of A wedge B should be, well, lambda of A wedge lambda of B back in this category. One other thing is that these are always, shouldn't be a finite, it should be a bounded finite distributive lattice. So the zero element is going to get mapped to the empty set, and the top element of this lattice is going to get mapped to the original chain complex X. So here's a picture to go with that. Here I have a lattice. Here I have a cell complex. I'm going to give you lambda now, and lambda says, well, take this element to this subcomplex, take this element to this subcomplex, take this element to the entire subcomplex. Again, lambda is supposed to be a lattice homomorphism, so where should A union B go to? Well, it should end up at this complex. The span of these two complexes, which in this case will be the direct sum of them. All right. So we will come back and see this picture in a dynamics context soon, but let me point out that the actual things that I care about in order to work with this lattice homomorphism is back to the post set P, right, that we got from looking at the joint irreducible elements. All right, so the post set of joint irreducible elements is the post set that somehow is going to be the indexing set for all the information that I care about in this chain complex. All right. Okay, so that was the mathematical background. I hope everybody stuck with me. If you've seen this stuff before, then you fell asleep because it's elementary, and if you haven't seen it before, then you might have fallen asleep because it's just a list of definitions. But let's now go to dynamics, all right? So I'm talking about, I'm not calling this a dynamical system, all right? What I'm about to tell you is not a dynamical system. I will care very much about how it relates to dynamical systems, but I do want to think about it as a form of dynamics. So I start with a cell complex. So I'm going to give you something that's purely combinatorial. So I start with a cell complex, and a dynamic clade is a bounded sublattice made up of top cells of the cell complex, all right? And that is supposed to give rise to a lattice filtered chain complex. In other words, I have a lattice homomorphism A from the lattice homomorphism from this lattice A into the lattice of subchain complexes. All right, and that's my notion of dynamics. Okay. Something I can derive from this very quickly is the Morse graph. I have this bounded, everything's finite, bounded sublattice. So I can use Birkhoff's theorem. It tells me things you should focus on are the joint irreducible elements. So this is a poset. Remember, a poset is equivalent to a directed acyclic graph, and so that's what I refer to as my Morse graph. So if I give you this the definition, then I can, and I give you the sublattice, then I can derive the Morse graph. For each poset, for each element in the joint irreducible elements, I'm going to talk about the associated Morse tile, and that is, well, you know, this is a sublattice of this poset structure in the cell complex, and so what I'm going to do is I look at, for every joint irreducible element, there is one of these subsets of cells. And because it's joint irreducible, it has a well-defined immediate predecessor. And so I can look at this cell complex, take away the cell complex that is associated to the or set of cells. This is on the cell level, not on the complex level. I can look at the set of cells, take away the set of cells from the immediate predecessor, and I'm going to call that a Morse tile. And then I'm going to define something that I'll call the Conley index, and that is just take the relative homology of this. Now we have to be talking in the chain complex level of the chain complex associated with this relative the chain complex associated to the immediate predecessor. All right. Okay, again, I want to repeat what I said at the beginning. I've given you a purely combinatorial definition. This is a definition of dynamics. It's not a dynamical system, but it's a definition of dynamics. And there is a little bit of linear algebra that I've thrown in at the end in order to be able to do this homology computation. Like I said, I mean, I really am interested in dynamical systems. So as I want, and I will spend majority of the rest of the talk talking about how this does relate to dynamical systems. But, you know, what should you have in mind? Well, you know, you have this cell complex. If you think about this cell complex, for example, being a simplicial decomposition of a space, then, you know, X would be the space that gave rise to the cell complex, right? So it's a nice topological space in the sense that it's something that's triangulable. The dynamic clade, where that comes from is, I want you to think about the lattice of attracting blocks, all right? So I'm going to come back and talk about this in a moment, what I mean by the lattice of attracting blocks, all right? So there's going to be a rule how you go from dynamic clades to dynamical systems and back again. But before I do that, I want to do a little bit more on the algebra. So in general, this cell complex is quite large. You know, you start with your phase space, you do a decomposition into, for example, triangles or cubes or whatever your favorite polygons are, or if you're, you know, capable of it, into a nice CW decomposition. In general, that complex can be quite large, and the question is there a minimal cell complex that captures all this information that's going to be in the dynamic clade? And the answer is yes, and we're calling such a complex a Conley complex. And so it's supposed to be a cell complex So I should have, I can, another way to talk about the cell complex would actually be to go to the chain complex structure. And so for the chain complex, I have to give you the boundary operator, and this is what we call the connection matrix. Notice the chains in my in this chain complex are the vector spaces that you get by computing these Conley indices. All right, so I have my clade, dynamic clade, which is this lattice. I look at the joint irreducible elements. For each of the joint irreducible elements, I can define something called a Conley index, and now I can take the direct sum of those. That is a graded vector space, and here's a boundary operator on that graded vector space. All right, boundary operator means it squares to 0, and it's a degree minus 1 operator. All right, so this is now a chain complex, and this is what we call the Conley complex, and this captures all the, you know, in its essential, all the information, the dynamic information from the clade. These turn out to be quite computable, surprising, and this is really due to Sean Harker and Kelly Spenlove. And I'll just mention that Kelly's at Oxford, a postdoc. Well, I think at the moment he's in Florida, but he isn't a postdoc at Oxford. And what they've managed to do is to compute connection matrices for 10-dimensional complexes, and these original complexes in the cell complex contain trillions of cells, and yet you get non-trivial connection matrices. So we can compute with these. And what I claim at this point is that I've solved the dynamics. All right, so the power of this is that we're working with something completely combinatorial, except for some linear algebra that has to be computed. So this is extremely computable. And what I claim at this point is that I have solved the dynamics. Now, okay, so I'm going to have to explain that to you and what I mean by that. All right. So when I talk about dynamics, now having solved the dynamics, I've done all the computations on the dynamic clade side. What am I telling you about dynamical systems that the vast majority of us are actually interested in? So what you should have in the back of your mind is some kind of compact metric space. In order to do the algebraic topology, it has to be nice enough that I can actually talk about, combinatorial algebraic topology. So think of a triangulable space, CW complex, and I have a dynamical system on it, either a semi-flow or a continuous map. That's where we've worked out the theory. There are two new, and you can see how recent they are because they're on the, the publications are on the archive. One is dealing with Filipov systems. The other is dealing with hybrid systems. And my belief is that they've done enough work that this rest of this machinery that I'm going to talk about will go through. But that's still just a hunch on my part. There is work currently being done by both these groups to try to carry out what I just said. Okay, so I had mentioned attracting blocks a couple of slides ago. So if I have one of these dynamical systems, then an attracting block is just a compact set so that immediately in time it gets mapped into its interior. So either under one iterate of the map or for any positive time you end up in its interior. Set of attracting blocks is a bounded distributive lattice. Okay, so that's not so difficult to prove, and this appears in a paper with Bill Calise and Rob Vandervorst, a formal statement of that. And again, what really needs to be done is theorems like that need to be proved in these settings up here. Okay, so I have a cell complex that decomposes my space. So I have a space and I have a triangulation of it.
But is it finite, this set of attracting blocks? It's usually have infinitely many attractors. So
I mean, this lattice is huge. This is an infinite lattice.
It's often infinite. Sometimes finite, sometimes infinite.
I'm sorry.
It is always infinite. Yes.
Yes. In any interesting case, this is a uncountably infinite many attracting blocks. Yes. Yes. Absolutely. This is huge.
Okay.
Yes. Yes, and I'm really, this is maybe at the end of the talk, if there's time, we can talk a little bit more about this, because this is where we start seeing the distinction between what we're seeing with the dynamic clades and what true dynamical systems are capable of expressing. All right. So I have a cell complex now that decomposes this space. How do I go from a dynamic clade to a dynamical system? Well, I declare this, I have the dynamic clade, so I have this lattice that I've just, declared to you, and I just say, okay, call this a lattice of attracting blocks. And what you end up with now is a huge class of dynamical systems, because what I've really done here is I've essentially said, look, any dynamical system where this object is a lattice of attracting blocks is a dynamical system I'm talking about. All right. And the other way around, if I start with a dynamical system, well, this is this, uncountably large lattice. Choose some finite sublattice out of here, and you should allow for the empty set in that lattice, and you should allow for the entire space in that lattice. But choose a finite sublattice of this, and now I have a dynamic clade. All right. Now, this is a huge lattice, and if I choose a finite sublattice of it, I'm only capturing a portion of the dynamics, right? So given a dynamical system, in principle, it could be associated to infinitely many fundamentally different dynamic clades. All right. This is kind of a statement about, when you choose this, you've kind of chosen a level, a scale at which you're studying your dynamical system. All right, let's be, what kind of dynamics can my dynamic clades capture? So let's stay a little bit abstract for the moment. So here's a theorem. An attracting block is a closed regular set. So if I was to work on a little bit more general, and I didn't care about the algebraic topology, but I was willing to work on the lattice of closed regular sets, then attracting blocks fit to this lattice. So we actually do have a very nice map between attracting blocks and these lattices of closed regular sets. What we're really typically interested in when we do dynamical systems is not the attracting blocks, but the invariant sets associated to it, which would be attractors. And as everybody I'm sure in the audience knows, an attractor is just a compact set with a property that it has a neighborhood such that the omega limit set of the neighborhood is the set itself. So this is an invariant set. All right. So if I give you a lattice of attracting blocks, then if I take the omega limit set of that attractor, I end up with of that attracting block, I end up with attractors, and the set of attractors forms a bounded distributive lattice. So that's actually a lattice morphism. And here's a theorem that if you give me a finite sublattice of attractors, all right, so we start with the objects of interest from the dynamical systems perspective, then there is a cell complex on your space, and there is a dynamic clade that you can choose such that the omega limit set of that dynamic clade actually gives you that lattice of attractors. All right, so in summary, what I'm claiming is that if you think about Conley's notions of decompositions, attractor-repeller pairs, Morse decompositions, that kind of information can be captured by dynamic clades. All right, so there is a lot of generality to dynamic clades and what it can capture. So the other point that I want to make from going from dynamic clades to dynamical systems is, I introduced that notion of Conley index, and that really is the Conley index. If you perform that computation, you will get the homology Conley index if you say that the elements of the clade are attracting blocks. And the Conley index lets you find lots of structures that are of classical interest, right? We can find fixed points, periodic orbits, chaotic dynamics. We can look at bifurcations. We can look at the global structure of attractors. So there are theorems out there that allow, in this sense, to say, oh, I've gone from the dynamic clade and all the algebra that I computed for you, and I can now tell you something of interest of any dynamical system that that dynamic clade defines. So the point of these theorems is that, homology, which in this case is the Conley index, plus something, typically for these results, you need a little bit more information, gives you some information about the dynamical systems, and this is dynamical systems information, right? And the point of the connection matrix is that kind of at the resolution that we're studying the system, the connection matrix allows us to compute all possible Conley indices of interest. So that's what I mean by saying that, after I've computed the Conley, the connection matrix, I have solved the dynamical system. By the dynamical system, I mean any dynamical system that's compatible with a particular dynamic clade that I chose. Let me give you a more concrete example. So I have my, here's a cell complex. All right, so out of that cell complex, I should pick my my dynamic clade. Let's, I've drawn a picture, so let's already think about the phase space that I want to be working on. This could be thought of as the interval from -4 to 4, where, the vertices are the integers, and then you get the associated cells. There's my phase space. I have to tell you my dynamic clade. So here's my lattice of attracting blocks. I've just declared, back here in this cell complex, that these are the cells that are going to, or these unions of cells are going to make up the lattice of attracting blocks. And here's my lattice structure, and I have, these elements in that lattice. Birkhoff says, focus on the joint irreducible elements. That's this element, that element. That's what we need to focus on. Let's look now at the Morse cells. So Morse cells says, let's, what did I do now? Let me get this back into proper. There. So the joint so the Morse tiles are look at the joint irreducible element and take away its immediate predecessor. So the Morse tiles are going to be for 1, the joint irreducible element associated to 1, I'm going to get, for example, the interval -3 to -1. For 2, I'll get the interval minus 1 to 3. There's obviously the union of them, which is this element in the lattice. And then there's the whole space, but the Morse tile associated to this element is take this set, the whole space, and take away the unions of them, take away its immediate predecessor, which would be the union of the blue and the green. And so we're going to end up with these 4 red tiles. All right. So those are the Morse tiles. I'm telling you, the whole point of this example is to say that I'm talking about dynamical systems. How does this relate, for example, to a differential equation? So I've got dx dt equals f of x. We're in 1 dimension, so let's just, for the sake of drawing simple pictures, let's take f to be the antiderivative of f. So we're talking with a gradient system, but it's a bit of a red herring, but it allows for nice pictures. The attracting blocks that we have are regions of phase space that are forward invariant in time. So if I, here are the demarcations of the Morse tiles, and if I look at my functional f, then the vector field is pointing in on these regions. And so, this differential equation corresponds to this dynamic clade. And from here we see bistability. What's nice about this is that I could have also used that function, or I could have used a much wilder function, and I'm still talking about, on this level of resolution, the same dynamics. And we can do the algebraic topology associated to it. There is the lattice filtration. We can, and there's an algorithm that gets you from this information down to the Conley complex. And here's the chain map for that, the boundary operator for that complex. And this information in here tells me that whatever invariant set is there, and it's got to be non-trivial, there are connecting orbits from this invariant set down to these invariant sets. And these invariant sets are non-empty because they're part of this chain complex. So their Conley indices must have been non-empty. If I want to go from dynamical systems to dynamic clades and then back to dynamical systems, here's a toy problem of data analysis. So I'm gonna run my time series. Each one of these is an initial condition. What I'm showing you now is in bigger and bigger balls is the images of these. What you might be willing to accept from this data is that those two boxes are trapping regions, that those are elements of my lattice of attractors, and then there's the full space that's an attractor. And so we're right back to the same algebra if we did this. And so this would say, well, there's going to be at least 3 invariant sets of interest in this dynamical system. There's the invariant set of interest in this region, the invariant set of this region. There's an invariant set in the complement, and there must be trajectories that go from the invariant set in the complement to those 2 regions. So we've gone from dynamical systems to a dynamic clade. We use the algebraic topology then to say that there must have been something going on with the dynamical system that generated that time series. And the only thing that we have to assume is that we believe that the regions I drew for you were really forming a lattice of attracting blocks. All right, so that becomes now a question from dynamics. Let me finish because I'm almost out of time. So I'm going to go from a dynamic clade to a dynamical system, and this is kind of machinery that we've been setting up. And I'm going to look at something that's the P53 network, and this is absolutely fundamental in the study of cancer. And here's here's what I read in papers when I read something like, here, a cancer cell, it's impossible for a normal cell to become a cancer cell unless it inactivates the P53 network. And then you look in the pictures that they have in the paper, because this is their model, and they show something like this. Here's another subnetwork of the P53 network. So what does this statement mean, right? So presumably there's some kind of differential equation that models this. There should be at least, if we're working with this subnetwork, there should be at least 5 variables, maybe the expression levels, protein levels of these genes. The way we're going to model it, we think there should be at least a 29-dimensional parameter space. But I don't know what this differential equation is. On the other hand, if you look at experimental data, and I think this is P53 and MDM2, their expression levels, one's measured in green and one's measured in red, and these are at different times, you see them oscillating on and off. All right, so presumably when the P53 network is working, what you're seeing is these oscillations, and that's the whole point of this paper, is suggesting that P53 controls cell development or cell reproduction by actually the frequency of the signal that it's outputting. So it really is very much a dynamical systems question. And so the first thing you could ask is, does this network produce the observed oscillatory dynamics, right? Now, I don't know what the differential equation is, but we can talk about dynamics from this dynamic clade perspective, all right? But to do that, we're going to have to be able to determine all the possible dynamics that this network can exhibit. And we're going to have, and then if there is oscillation, if I want to talk about inactivation, then presumably what's happening is that the cell is operating at different parameter regimes. And so I need to understand how this dynamics is related to parameters. And to solve this problem, we've developed software, and we call the software DSGRN, short for Dynamic Signatures Generated by Regulatory Networks. The input for the software is this network. And if you were at my Fields Institute talk, then this was what that whole talk was about. What is this machine and what does it do? The output is going to be a database. It's an explicit decomposition of parameter space. Like I said, this is a 29-dimensional parameter space. We have an explicit decomposition, finite decomposition of it. And to each parameter region, we have a description of the global dynamics. What I would really like to write down here is, to each parameter region, we have a clade. I didn't write that down. I'm trying to be truthful. The software at the moment does not produce a clade. I'm hoping that we will produce Clades from this software before the pandemic is over. So, I mean, however fast we can get a vaccine out, I'm hoping we can do this faster. And this database is now queryable. So we have a 29-dimensional parameter space. DSGRN for this particular network divides it into 800,000 regions. The dynamics is computed for every single parameter region. And because it's purely combinatorics, this can be done extremely fast. The total cost for computing this database on 800,000 regions in this 29-dimensional parameter space for this 5-dimensional system is 37 seconds on a laptop, right? So this is a minuscule computation. Everything can be done in parallel. So, you know, working with hundreds of billions of cells, of regions and parameter space is something we can do, and we've worked in 50 and plus dynamic dimensional parameter spaces. So we can really do what I think are large computations pretty efficiently. Basic question, can this network produce oscillations? The answer is yes, and it does it for about 7,000 out of these 800,000 regions. If this oscillation is supposed to be really stable, maybe there's some stuff missing, because that's a pretty small portion of parameter space. Cells are pretty noisy, so maybe there's better controls that are going on, and we need to look for more nodes. We have an explicit representation of parameters for each of these regions. Biologists often write down models, differential equations models of this that involve Hill functions. So what we can do is we can choose a particular parameter value, and then we can evaluate this and ask, do we see oscillations? And the answer is yes. All right. And so not for every single parameter regime, but it's and that now gets into details about why you shouldn't expect for every parameter to get this. But in general, this is a very good indicator of where you should go to look for these kinds of oscillations. And I'm a little over time, but I started a little bit late, so that's my excuse. This is joint work with a lot of people. As you've seen, for this theory, most of the work has been done with Bill Calise and Rob van der Vorst, though I should also mention Thomas Getty and Hiroshi Kubo and Hiro Oka. And of course, you saw some of the work of Kelly Spenlove. But a lot of the details, for example, the DSGRN software is really being done by Marcia Gamero, and they're, yeah, I'll stop here with that. All right, thank you very much.
All right, thank you very much. Any questions?
Sorry, about the last slide. You say that input is a graph, not system of differential equations. But then you have some parameters, or I missed something.
Yes, so what kind of parameters do we use? So, you know, I need to somehow, okay, so I have a clade here. How do we get the clade? We get the clade by actually first computing the Morse graph. How do we get the Morse graph? We get the Morse graph by looking at a state transition graph. So what we do is we have, you know, the positive orthant in R5. The way we build models for this is that we say that, you know, ATM is supposed to be activating P53. So I should look at so the way I'll model this is I'll say that there's a low level of activation, there's a high level of activation, and there's some value at which, some threshold at which you change from low to high. So think of it as a step function. That is used then to determine whether one box moves into another box or not. So that becomes now a directed graph. In that directed graph, we look for recurrence and non-recurrence, and from that we derive a Morse graph. From that Morse graph, we then can look at the lattice of downsets, and that, it's not quite a dynamic clade. We know how to make it into a dynamic clade, but that is not in the software right now. But the parameters, therefore, are for each node, there's a decay rate, and for each node, there is a low impact of expression, there's a high level of expression, and there's a threshold at which you change from low to high. And that's how you get, so for every edge, there's 3 parameters, and for every node, there's 1 parameter, and so that's how you end up with a 29-dimensional parameter space.
Okay.
Any other questions?
Hello. So have you looked at like random systems or systems with noise, or how does this kind of like fit that kind of world?
So I would love to do something like that. I don't have, that's a little out of my expertise, but I'd like to think of it as follows. If I think about the instantiation of the dynamic clade, so I have my cell complex, and I tell you, yeah, let's go back to, this toy example back here. Okay, so one comment is, when I ran this simulation, this is a really trivial ODE, but I did put a lot of noise in it. Okay, so, but you don't see that, and that's the whole point. Okay, now it was bounded noise, so the notion of trapping regions still makes sense. But let's think about this example right here. Here I have these regions that are these are trapping regions, right?
Yeah.
So if I had bounded noise, then in some sense you could think of this as being bounded noise. So the theory will go through as long as these regions are big enough to capture the bounded noise. And if you had a stochastic process, then there should be some theorems that tell you, expected times that you would see this particular lattice structure, right?
Right.
And I would love to know how to properly formulate that. Right? An alternative idea, and this is something we are exploring a lot, is, and again, this is kind of out of my expertise and I'm trying to learn that. But if you think about, instead of, when we think about dynamical systems, or at least when I think about dynamical systems from my background, right? I think, oh, the space of family of dynamical systems is you pick your manifold and you look at all C1 vector fields on that manifold, all right? Another way to think about it would be to say, okay, you've given me the data, for example, the data in that, this example. Imagine that there's a Gaussian process that would represent the data, right? So now instead of the set of vector fields being chosen from the C1 vector fields, I would think that this is an instantiation where it was given to me by a Gaussian process.
Yeah.
Okay, if I use a Gaussian process, then I know something about, the standard, the variation, right, or the standard deviation, right? So I could sit down and say, okay, here's the data I've been given, here's the standard deviation associated to that data. I think it's the case then that if you gave me that information from the Gaussian process, then if I build a lattice of a clade, right, where for one standard deviation, this represents the Gaussian process. Think of it as a map. The Gaussian process is telling me how I should map. Then I think you get a theorem that says that if this is your data and you chose this as the dynamic clade and it fit within one standard deviation, then the probability that this is the dynamics you will see is what is it, 66 or some percent, right? That shows you how good I am at right? So I think there is room to try to mesh this with stochastic processes, but that's really not a place where I have much expertise. But that is something I'm very interested in and trying to think about that right now.
Yeah, maybe this could even like be a bridge, like connecting the kind of unbounded or stochastic noise with the bounded, because like you could do like probabilistic clades, but then on the other hand, like with the bounded noise, you have some, you have these bounded regions which maybe kind of like more naturally connect with this kind of these regions, let's say the trapping regions. So
right, because the dynamic clades, I mean, if you think that there's limits to your measurements, then that really is what got me onto the dynamic, onto these lattices. I mean,
Yeah, exactly.
that's if you think about where did I get all these points? Well, if I had a measurement that couldn't be better than a half, then this is a natural kind of decomposition of my space. Okay, so now I have a tiling. It's a finite tiling, and we can talk about, like you said, the set of random clades that are possible. What are the set of we could write down all possible lattice filtered complexes. Now we could put a weighting on those, and now that is a distribution of the dynamics you could see, and all the machinery, of course, goes through, and now you'd have a probabilistic statement of it.
Yeah, that would be quite exciting.
Yes, I'd love to talk to you about that. I mean, this is really what I'm trying to understand right now, and so yeah.
And so I'm a PhD student here at the Imperial with Jeroen and Martin. So we're looking at bounded noise stuff. So yeah, this is quite interesting. I had no idea about this stuff before.
So let's keep talking.
Sure.
All right. Any other questions? Okay, so let's thank the speaker again, and thanks again for coming. Thank you.
My pleasure. And nice to see some of you, even if it is very long distance. All right. Take care.
Yeah, thank you.
Thanks.
Thanks.
Good, nice talk.
It was nice, isn't it? Yeah. Quite deep, so I think there is a lot to digest here.
There's a long history of these things, right? So come on for a long time.
Yeah, they have been going on with also that even Marian Rosa came in. So yeah, so they have been around for a long time, but it seems to be a very deep, a lot of technology going there. Apparently, even I mean, remember Sameh that we met in from Polytechnic? He was telling me that they okay, see, Marian Mozak is back. I don't know what. Yeah, okay, so
because I also was talking to Kokubu a little bit about this, because he's working on this stuff in Kyoto, and yeah, kind of, he does this thing also, but he's not so religious about these things, right? So he also, there's a certain, they have been on this for like decades, but I think it's not been so practical somehow. So and it would be nice to see if actually at some point it becomes more practical. And I think the computational, because sometimes this topological stuff is just basically elementary. So then there come statements that you can actually deduce rather easily in other ways as well. But maybe the trick is if it becomes really non-trivial and becomes really complicated, then you can still extract some meaningful. Because it's a little bit of trick. I think also he said at some point you model then the dynamics with some simple. They actually put some simple models on it in the end, right? So
yes.
For these networks, there's a couple of parameters and so on, and they basically presume that it's some kind of simple internal model.
Yes, yes.
So Kokubo was explaining this to me somehow, that in the end somehow they then assume that somehow there's a topology, but then it's underneath there's some kind of like very simple dynamics.
Okay.
The equations is so there's a certain.
So it's not as general as one may think, because I thought that they were like so there is something hidden there, which is like that is like simple.
Oh, there are many degrees of freedom, and you play a certain trade. So they try to get this kind of global stuff, but then on the local level, I think that the equations, but each of these cells is doing, for instance, in this 29 parameter thing is some kind of rudimentary. Maybe that's the right attitude. I don't know if you want to understand what's going on. So, but if that has very non-trivial behavior, you of course never get there. So,
I see. Okay.
So yeah.
So there's something there, because but it just seems to be like nice.
I think there's some practical factors that if things are not elementary, if things are not essentially simple or reducible to something relatively simple, then we cannot understand. We cannot understand it so much. So there has to be some presumption of finding the simple rule or the simple approximate rule. There can't be the presumption of let's find something very complicated.
Yes, that's right. Yeah.
It should lead to a fail in some sense. That you try to find something simple and it fails. But yeah, also there's all the machine learning stuff. Also, again, you hope for something simple that pops up. If it doesn't exist, and then maybe you ask the wrong question or so, or I don't know. The question is like how much, yeah. But of course we can our what we can do for complexity ourselves is limited to some extent, that we can then use computer to reach in those directions where we are limited. So maybe some things we're very good at, like remembering faces and stuff like that. But some other things we're notoriously bad at. So maybe we can complement.
Yeah, but also like what the question that Ken asked about the connection with random dynamical systems, and maybe you can be able to do a partition of the phase space, or I don't know, compute this.
Yeah, I think that he asked like what is dynamics, and he says like maybe you can look at it from this graph point of view. I think the question that I was asking earlier, and we talked a bit about it, like can you think of this not guessing the dynamics but guessing some kind of random dynamics? Is there another way, other classes you can put on and say like have some data? Does it look like something? Whether this is and then he says Gaussian processes or whatever. It's just everyone's flavor. And it's a good question to say, like, if you have certain data, can you make any kind of like sensible statement of whether certain type of models are better or worse to represent such data and draw conclusions from it? Yeah, but it will be it's partially conceptual and partially engineering effort. Like airplanes fly because of engineers and some reasonable physics ideas, but the first the fundamental ideas don't make the thing fly.
Yes.
It flies only after considerable tinkering at the details.
Yeah.
So it has to be combined effort somehow. But it's interesting. It's really it's interesting. I think the ambition level is going up, so that's good. I find that.
Yes.
Because computing is becoming just better, and people program very complicated things now very quickly, and it runs fast, and so this is just a scale. It's not a fundamental difference; it's a scale difference. It means that the kind of things you now can do routinely, he can run something on his laptop. He couldn't run that 15 years ago on his laptop at all.
Yeah,
he probably couldn't find any machine that could run anything somehow. So this makes a huge difference. And the question, like, what can you which kind of problems can you now attack with methodologies, and but it also becomes very complicated. So who's going to understand many of these things? So this is going to be in the background of something. So this is not just there's still some algebra, but it's not the usual some eigenvectors or some matrices.
Yeah, exactly. But yeah, I'm like I try to understand it myself, but I never. I was I think I need to ask him just like, if you have a specific simple model, like transcritical bifurcation or like an OU process. Okay, how would you keep track of all these terms, and what can you do about this? But it's not. Yeah, it's not. But still, it's still linear algebra. That's the thing. Is that it's still linear computations. Yeah. So this.
Well, you win some and you gain some. You give up something. Of course, to talk about understanding bifurcations in this context and using his is also problematic somehow. So yeah, I don't know.
Yeah, I also don't. I mean, it just seems elegant, but then what's the deeply within?
I think the problem is all this stuff. I think at least from Mischaikow, I've seen Mischaikow. I think the first time in '98 when he just proved something about Lorentz, the computational proof of Lorentz being chaotic or something. Also using this kind of Conley index, and so he came to Houston, and he was not such a big shot at that time, but definitely doing well already. But he mainly be pushing that agenda. So that was a huge thing that he could do some combinatorial stuff and then show that somehow you have non-trivial dynamics. Like that's a non-periodic orbit and stuff like that. But a lot of this other stuff has been very elegant in some sense. That there's a lot of like theory going in the background, and most of the theory, of course, already exists. So there's a lot of this algebraic topology that just exists. It's not, they didn't invent it, right?
Yeah, exactly. Yeah.
But now the question is like, kind of, does it do anything useful or theoretically really exciting and interesting? And I think things have been moving somewhat slower than they promised. So I think that at some point, he's been at Rutgers forever, and the idea was, of course, that he would help unravel these pathways in all kind of biological processes and so on. And I think they're still not there somehow. So yeah. So this is really what the promise was, that they can somehow unravel these things, and they can process all this kind of like enormous amounts of data from genetic experiments and so on. You can actually show pathways, and then you can actually use that to control things and make people better and understand disease and understand functioning biochemical processes. And who knows, maybe this is the way. So it's basically very complicated networks and very simple dynamics on it. Actually, that's the idea somehow. But I think it's not there. So and he doesn't. We talk to Google and say, we don't, we're still far away. But maybe there are many different mountains to climb in the meantime. So.
Okay.
By the way, I need to kind of run because I need to bring Jens a bicycle at school, and it's kind of 5 minutes.
All right, then. Thank you.
Yeah. Okay. See you.